Every time you log into a website, something stands between your account and an attacker. It is your password. Passwords are not magic. Given enough time and computing power, almost any password can be cracked. The method attackers use most often is called brute force. In this video, we will break down exactly how brute force attacks work, what makes them fast or slow, and what actually stops them. We will also look at the decisions developers make when storing passwords and why those decisions matter enormously. Let us start with the basics. When you create a password on a website, the website does not store the password itself. It stores a hash. A hash is the output of a one-way mathematical function. You feed in the password and you get back a fixed length string of characters. The same input always produces the same output, but you cannot reverse the process. You cannot take the hash and work backwards to find the original password. So when you log in again, the server hashes what you typed and compares it to the stored hash. If they match, you are in. If they do not match, access is denied. This design means that even the company storing your password cannot read it. If the database is breached and an attacker downloads all of the hashes, the attacker still has to figure out what passwords those hashes correspond to. And this is exactly where brute force begins. A pure brute force attack tries every possible combination of characters. Start with a single character, lowercase a, then b, then c, all the way through the alphabet. Then try a back, then a, and so on, systematically and exhaustively. Given infinite time, brute force will always find the answer. The question is how long that takes, and whether the attacker has that kind of time before the stolen credentials become worthless. The search space grows exponentially with password length. A password using only lowercase letters has 26 possible characters per position. A one-character password has 26 possibilities. A two-character password has 26 squared, which is 676. A six-character lowercase password has 26 to the sixth power, about 309 million combinations. That sounds like a lot, but a modern GPU can compute billions of hashes per second. At those speeds, 309 million combinations is exhausted in milliseconds, not hours. An 8-character password using only lowercase letters has about 209 billion combinations. Still crackable in minutes on modern hardware. Add uppercase letters, digits, and symbols, and you expand the character set to around 95 printable characters. Now an 8-character password has 95 to the power of 8, which is about 6.6 quadrillion combinations. At 1 billion guesses per second on a single GPU, that is roughly 76 days. But dedicated cracking rigs running multiple high-end GPUs process hundreds of billions of hashes per second. Suddenly 76 days collapses into hours. This is why password length matters far more than character variety. A 12-character password using only lowercase letters has more total combinations than an 8-character password using every uppercase letter, digit, and special symbol available. Every character you add multiplies the search space by the size of the character set. Length is the single most important factor in a password's resistance to brute force. Attackers rarely do pure brute force from scratch, however, because smarter approaches find passwords much faster. Dictionary attacks use precompiled lists instead of generating every possible combination. Databases of billions of real passwords compiled from historical data breaches are freely available to researchers and criminals alike. The attacker hashes every entry in the list and compares it to the stolen hashes. Common passwords like 1, 2, 3. 4, 5, 6 password Cordy let mean and I love you are found immediately. So are names followed by birth years, or the names of sports teams followed by exclamation points. A hybrid attack goes further by combining dictionary entries with transformation rules. Capitalize the first letter. Add a number at the end. Replace letters with visually similar characters. The word password becomes P4SSW0ARD. The phrase correct horse battery staple becomes a concatenated string with digits inserted. These substitutions feel clever to the person choosing them, but they are so predictable that modern cracking tools include entire rule sets built around common human substitution patterns. Tools like Hashcat ship with hundreds of built-in rules that encode the most frequent transformations real users apply to real words. If your password is based on a dictionary word with some letters replaced by numbers or symbols, a hybrid attack will find it in seconds rather than days. The attacker does not need to be clever, they just need to run the right rule set. The speed of all these attacks depends critically on which hashing algorithm was used to store the passwords. MD5 and SHA-1 are general-purpose hashing algorithms designed for speed. They work well for verifying file integrity, but they are disastrous for storing passwords. A single consumer-grade GPU can compute roughly 10 billion MD5 hashes per second. If a database of user passwords was hashed with MD5, an attacker with a few GPUs can test every common password and most short passwords within hours of obtaining the stolen data. Algorithms designed specifically for password storage work vary differently. bcrypt, scrypt, and argon 2 are intentionally slow. They are tuned to require a meaningful amount of computation time and, in the case of scrypt and argon 2, a meaningful amount of memory per hash computation. bcrypt on the same hardware that computes 10 billion MD5 hashes per second might allow only around 10,000 bcrypt guesses per second. That single algorithmic choice stretches an attack that would take hours into one that would take centuries. The algorithm itself is the most powerful defense available to a system architect. These slow algorithms also incorporate a mechanism called salting. A salt is a randomly generated value created fresh for each account and combined with the password before hashing. Two users who choose the exact same password end up with completely different hashes because their individual salts differ. This defeats a class of attack called rainbow tables. A rainbow table is a pre-computed database mapping millions of common passwords to their hashes. An attacker who has one can look up a stolen hash instantly without doing any computation at all. With unique salts, rainbow tables become useless. The attacker must compute fresh hashes for every target password every time, with no possibility of reusing prior work. From a systems design perspective, stopping brute force attacks requires multiple layers working together. Rate limiting is essential for online attacks, where the attacker is submitting guesses through the normal login interface rather than operating on a stolen offline database. After a small number of failed attempts, the system slows the attacker down. Lock the account temporarily. Require an email verification step. Apply exponential backoff so each subsequent failed attempt takes longer than the last. These measures make automated online guessing impractical without significantly inconveniencing legitimate users who simply mistype their password. Account lockout must be designed carefully, however. Locking accounts too aggressively creates a denial of service opportunity, where an attacker deliberately triggers lockouts on every account in the system just to prevent any legitimate user from accessing the service. A better approach is soft lockout combined with continuous monitoring. Flag suspicious patterns, require additional verification when anomalies are detected, and alert the account owner rather than hard locking indefinitely. Multi-factor authentication fundamentally changes the threat model. Even if an attacker successfully cracks or obtains a password through a breach, the second factor is still required to access the account. The password becomes one layer in a defense in-depth model rather than the only barrier. Time-based one-time passwords generated by an authenticator app cannot be brute forced across the network because they expire every 30 seconds and the window to use any given code is too short for an automated attack to exploit. For developers, the most important implementation decision is selecting the right hashing function for storing passwords. The answer in every modern language and framework has a clear recommended default. In Python, you use bcrypt or argon2 through the passlib or argon2c5 libraries. In Node.js, use bcrypt through the bcrypt.js package. In PHP, the built-in password underscore hash function accepts PASSWORDBCRYPT or PASSWORDARG. ON2. ID as algorithm constants and handles everything else for you. These functions manage salting automatically. You call one function to hash the password when the account is created, and a separate verification function at login time. All of the complexity, the salt generation, the iteration management, the encoding of the output, is handled internally by the library. The work factor in bcrypt is a tunable parameter that controls how computationally expensive each hash computation is. A work factor of 10 means the algorithm runs 2 to the power of 10 or 1024 internal iterations. Increasing the work factor to 12 makes each computation roughly 4 times slower. As hardware improves over time and the cost of computing hashes drops, you can increase the work factor and your stored password database remains as protected as before. Existing stored hashes do not need to be migrated in bulk. You simply update the work factor in your configuration, and the next time each user logs in successfully, you rehash their password with the new setting and store the updated hash transparently. The lesson from studying brute force attacks is that security is not about being theoretically unbreakable. It is about being expensive enough to break that the effort exceeds the expected values of the target. A randomly generated 16-character password stored with argon2 and a unique salt protected by rate limiting, monitored for anomalous login patterns, and backed by multi-factor authentication is not impossible to crack in an absolute sense. It is just impractical enough that an attacker with finite time and resources will move on to a softer target. Defense is a cost equation on both sides of the equation. That is how hackers crack passwords and how well-designed systems are built to stop them. Thanks for watching.